Well, hello everyone and welcome to part 4 of our videos on the chapter 8 material. This will be first of 3 videos, little short videos on this section where we continue to look at adding a molecule across a carbon-carbon double bond, elements of X and Y. The first couple of examples we'll look at here are where both partners in that X and Y molecule have the same atom. And so we'll take a look at a couple of examples of that. The first example we'll look at is one, in fact, that we've already seen before in this course. We introduced catalytic hydrogenation when we started discussing the relative stability of carbon-carbon double bonds. That's how we get that information, the heat of that hydrogenation. But that's formally an addition reaction. We didn't call it at the time, but now that we're getting a little more systematic about it, we can call it an addition reaction. And so here we see a carbon-carbon double bond, a molecule of H2 gas being added across it, and a catalyst of some kind. Platinum or palladium, or there's a few other more exotic catalysts, but those are the two main ones that we can use for this particular reaction, and just reduces that double bond down to the fully saturated bond here. So I think we've seen this in a little bit, or seen this before, like I said, when we were looking at carbon-carbon double bond stability. We can add some more new detail at this particular point of our examination of these, where if we look at a substrate like this, where we've got different participants across that double bond, what we observe is that those elements of the hydrogen both appear, if we look at the product, that is the two hydrogen atoms that we introduced from that molecule of H2 wind up on the same side of the molecule. So we get what we call so-called syn addition. So we get two molecules that are in fact enantiomers with respect to each other. If we look at those two molecules, we see that they're enantiomers of each other. We'll be looking at the stereochemistry of some of these addition reactions in the next couple of videos as well in some detail. So we get both enantiomers that occur in this particular reaction. So here's our explanation for that observation of this. What we think is that that platinum surface where that molecule of H2 sits on, again, the mechanism is a little bit different than what we've seen before, where it's a sort of adds to the double bond. In this case, that molecule of H2 gas requires that platinum or palladium catalyst. And what it does is it adds on to that platinum surface in a fashion like this. So activates that bond. It breaks the covalent hydrogen-hydrogen bond, makes an attachment to the platinum surface. The details of how this particular attachment takes place we might leave for a later course, but just to say that it happens here. And so that's our explanation for that syn addition, is that our molecule with the double bond, and I'll just try and draw it in here in a way that sort of shows this. If we've got ethyl or methyl, and there's that double bond, and the rest of that ring structure kind of going into the background. So just trying to represent that sitting flat over that platinum surface. What you can see then now is both of those hydrogen atoms would come in from the same side. They would get released off the platinum surface and add into that double bond. Again, the mechanism of that is something we'll leave for a different course, but just a bit of an explanation for them coming from the same side. So I can even potentially just draw an arrow to this and an arrow to that. Not implying a mechanism, but just saying that that's that intermediate where that sits over on the same face. So both of these attack from the same side of that pi bond. We get that stereochemistry, that so-called syn addition, and we wind up generating a pair of enantiomers. And so again, I'll make this very brief because we've already seen this particular reaction before. So we'll stop this here and we'll pick up looking at this when we're looking at now both X and Y are halogen atoms next.